You can start your lecture.
Okay, perfect. Dobrochotnaya, I would like to say to you. So good afternoon from Düsseldorf, Germany. It's also very nice to be again back to you for a presentation, for a teaching lecture on the topic progressing with physical organic correlation studies from the ground to the excited state. And I would like to share with you some ideas we have been developing over the past years it's a more or less like a semi-empirical approach where we collect data and try to get a deeper understanding of electronic structures. So this teaching seminar is of course predominantly dedicated to physical organic chromophore chemistry. So you will not see any kinds of syntheses today, but I would like rather to share with you some general ideas on the issue of how we explore chromophores. So first of all, I've also to check with the laser pointer. Yes, it works. And here is the table of contents I would like to share with you today. So first to talk with you and also to recap with you some aspects of physical organic chemistry. Whenever we talk about structure and properties, we want to find some kinds of correlation that is already embedded in the structure of the molecules. So is the structure of the molecules already telling us some kind of aspects how the compounds will react, or in terms of materials, how they will behave, what kind of properties they might have, especially electronic properties. And of course, this starts in a very classical sense with the so-called Hammett correlations, which you presumably still remember from your textbook organic chemistry from the beginning. And then I would like to share with you some structures, how structures affect the properties of chromophores. What are the most important aspects that have to be considered? And then in case-by-case studies, I would like to show you these aspects in several examples from my own career. So this also takes me back some more than 2 decades when I started in organometallic chemistry with my habilitation, where I already was dealing with chromophores. And then I progress a little bit more to modern aspects of our chemistry, which deals with phenothiazine. You might also know about our phenothiazine chemistry. So very electron-rich heterocycles. So as a representative of a strong donor in a chromophore system, as well as coumarines, which we have conversely used as acceptors in fluorophore systems. And I also would like to tell you a little bit then about indolones and also our relatively young children in the series. These are quinoxylines, namely speaking, 3-ethynylquinoxylines. And of course, I would also try to share with you several aspects of different behaviors of pi systems, not only as chromophores, but as fluorophores, or fluorescent compounds, as well as in the case of the phenothiazines, always as electrophores, where you have reversible redox processes that are also involved in these materials. And then at the end, I will give you a short summary. So I have compiled this lecture in the sense that you also can do reading for your own. And I also tried to compose complete sentences, not only flash words, so that you can really read through the text, but I myself will try to wrap up these things a little bit more quickly. And you not necessarily need to read every word that is written. So I will give you a brief focus on the topic I have prepared for you. So, of course, one of the golden threads of chemistry, as I told you, can we recognize, derive, quantify any kinds of the molecule's properties from its structure. And that immediately leads to the questions, of course, what are structure property relationships for a compound class? And can we rationalize, quantify phenomena we observe for later application? And of course, can we make predictions? Predictions is also something that is extremely valuable in an empirical science as chemistry, because you don't want to exploit any kinds of possibilities that are out there, because there are simply too many opportunities you have, and time is limited, and also our resources are limited. So we need to have some kind of smart approach, how we could come up with suggestions, how to exploit, for example, materials properties. Yeah, here I gave you some information about why is it so important that we have a prediction of functionality of molecules. Not only in biological systems, that's important, for example, with APIs, but also in the field of novel materials, which are more technically oriented. And all these contributes, of course, to societal needs that we all have to meet with doing science, because ultimately we are also being financed by public sources. Therefore, we need to provide these kinds of things. And so I would like to take you on a little journey back some 90 years ago. So to go back to the 1930s in the United States, when there something like physical organic chemistry was starting. So the reasoning was still very premature, and of course, because there was not too many appropriate physics available, and also mathematical backgrounds among chemists were a little bit underdeveloped. Nevertheless, analytics were developing, and that also gave an entry to the field of physical organic chemistry, which started right in these days. And at that time, of course, the chemists were always interested in finding a deeper sense in what they had discovered. Not only that they were compiling facts, like the biologists did for a long time, collecting plants and naming them and performing some kind of taxonomy, but rather like in physics, because physics was a big role model also for chemistry in the first half of the 20th century, that based upon reasoning and rational grounds, first principles, that one could derive insight in what nature is, and especially in the case of chemistry, how we can control nature, and that these laws need to be unraveled and also be discovered. And of course, everything what chemistry is doing is far away from simple. I mean, it's not necessary to tell this to you as chemists, but you can easily imagine that we are not dealing with single molecules per se in a completely isolated environment, but we are rather dealing with systems. So we are operating either in the solid state, we are operating in solution, or even in the gas phase. You could have interactions. So chemistry, to my opinion, and I think this is also holds true, is far more complicated than physics, because there are so many things to think about. And you can easily imagine that if you go to biological systems, it becomes even more complicated. So therefore, I would like to take with this tutorial an attempt to give you a physical organic introduction what structure property relationships in chromophores could be. As already mentioned, that Hammett was at the Columbia University in the 1930s, accidentally, I would say, or let's say more or less by curiosity, he made an interesting discovery by taking a look at two different reactions. So the one reaction is the acidity of benzoic acids, substituted benzoic acids. And you also know that from introductory chemistry, you can determine pKa values from that. So that's the equilibrium constant that can be determined by titration experiments. And he also then did another similar experiment where he took a look now not at the equilibrium, but rather at the rate constant of the saponification of ethyl esters of these benzoic acids, so substituted benzoic acids. And thereby he made a very interesting discovery, that there was indeed a correlation this was an empirical correlation, a semi-empirical correlation, as you can see here by plotting the log K X substituted benzoic ester, the rate over the proton derivative, that's benzoic acid itself, ester itself, plotting this logarithmic fraction over the logarithmic fraction of the equilibrium constants of the corresponding acids. And there he found a linear correlation, as you can see here. So they nicely lie on a line, and thereby you could also, of course, determine a linear equation, which is simply given by this Hammett equation. So a very fundamental equation. And the bottom line, what you could extract from that is that he had indeed found semi-empirically a correlation between thermodynamics, which comprises everything we know about structure, with a property that deals with kinetics. So that's a unification, more or less, between thermodynamics, which deals in equilibria, and kinetics, which ultimately, of course, is dependent on rate constants and, of course, how fast processes occur. And if you then take these information, then you can also easily see that there is a correlation between the delta delta G and the delta delta G dagger, which is the activation parameters. And therefore, it also has been named free linear enthalpy. That's the linear enthalpy relationships that were established. And I mean, if you are interested, there's an excellent German article on that in Chemie in unserer Zeit. That's a journal which, of course, is available in German, but I think you can also download the PDF file from the internet and easily also get it translated, for example, by Google Translator or DeepL or whatever you take. It tells what happened after 50 years with the Hammett equation. So that's the title, the Hammett equation, and what came out of it 50 years later. I think this is an interesting aspect because that's also beyond Hammett's lifetime. So he never thought maybe what could have been done with that. So this was the first starting point where there was found a correlation between structure and a property. In this case, the saponification rate of benzoic esters. And once one is going now to explore that, then one can easily see also that their substituent parameters can evolve if you plot the logarithm of the quotient of the equilibrium constants. And you simply set this arbitrarily to 1. The slope is meant to be 1. And this tells you that you will get the sigma x value. Sigma x is more or less a substituent parameter where x is the substituent you are considering. And this is more or less the foundation, of course, of the Hammett equation. And it also is valid for everything which is a meta or a para substituent in a benzoic system. So this makes more or less a foundation of the whole principle. And interestingly, of course, according to Hammett's equation, you have the same relationship of the rate constants. So again, the logarithm of the quotient of the rate constants of substituted and unsubstituted benzoic derivatives, you see more or less the same form. So also this depends on a substituent parameter. In this case, the rho value is the so-called reaction parameter. And of course, this reaction parameter can vary. It depends on the reaction you're considering. For example, if you're considering the protolysis, the simple proton abstraction from a benzoic acid, this has been set to 1, and then you can, of course, compare reactions which have different rho values. And these rho values tell you a little bit about the transition state that has to be passed by. So at that time, there was nothing like femtosecond spectroscopy, where you could have ultra fast time resolution of chemical processes, but you only had the possibility to take these kinds of kinetic measurements and finally extract from these correlation studies, you could get information on the rho parameter. For example, if in the transition state it is necessary to either stabilize a positive charge or a negative charge. So everything holds true for polar substituents and also for polar reactivity. And therefore, it could be then developed. And as I already told you, a linear free enthalpy relationship allows more or less to combine all kinds of structural information, which is embedded in everything that is thermodynamic, like structure, conformation, energy, with reactivity, so that you have, for example, also the possibility of estimating what is going on in reactions. And this is also particularly valuable if you're considering chromophores, because also with chromophores, you might get some kind of correlations if it shows any. And then you would also obtain slopes like this rho values, which could tell you a little bit about the general behavior of a chromophore. Over time, because it was coming back to the initial idea of Tufts and of Hammett's correlations, it was necessary, of course, to refine everything, because the initial Hammett correlation situation was relatively complex, was relatively simply held, and many things were simply neglected. As you also can see, there's no aspect of orthosubstituents, which is to some extent, of course, understandable because you have steric effects. But nevertheless, people like Taft, for example, Robert Taft, he was interested also in pinpointing down what steric effects are, and thereby he used the Hammett correlations also to derive steric parameters. And that also then gave a possibility to even have a hand on what is going on with steric effects, which sometimes, of course, are quite determining and pretty important with all kinds of chemical reactivity, and not only for that, but also for materials. Okay, so if we take substituent effects, then we can distinguish between steric effects on one side, but of course, we can also take a look on electronic effects. And in some cases, we have the combination of both. For example, if we have orbital interactions in a certain configuration or conformation, simply think about the sugars, where we have the anomeric effect, for example, alpha versus beta orientation of the hydroxy group at the anomeric center. This is clearly an aspect of stereoelectronics. And therefore, if you want to really consider electronic effects, of course, you can consider them as a combination of resonance and polar effects. Polar effects are more or less based upon electrostatics. They can act also through space. They don't have a long range for action. So usually they drop with Coulomb's law. Yet they are being described as so-called inductive effects because they can be also operate through bonds. So that's a little bit different between simple electrostatics and inductive effects, because inductive effects always have to take a sigma bonding system to operate, whereas electrostatic effects can be present anywhere. Nevertheless, they can be, of course, distinguished from resonance effects, where you can have a considerable long-range operation of the electronic information. This has been relatively precisely determined in the 1990s with anions and the carbon NMR spectra, because NMR spectroscopy is particularly sensitive to, in the Ramsey equation, to the paramagnetic shift tensors. And these are indicative of, let's say, distribution of charges. And one can say nowadays that the resonance is operating at least for 15 double bonds. This is quite a distance where you can say that the idea of a resonance structure is indeed also physically justified. It's not only what chemists have thought about, but it's also physically realistic estimation that one has, let's say, a resonance structure delocalization. So delocalization of pi electrons is important. Of course, sigma electrons can be also delocalized. Nowadays, we know that this is possible. Nevertheless, field effects that are based upon the sigma system, they decay with the Coulombic law, and they are therefore short range in comparison to resonance effects. We can, in most cases, consider them to be operative immediately and without any decay in the normal molecular dimensions we usually have to deal with. So, of course, you know from the textbooks that electronic effects can roughly be divided into resonance and inductive effects, so field effects and mesomeric effects, either designated with plus or minus m, depending on whether a positive or a negative charge may be accommodated. And the same holds true with inductive effects. So the operation through the sigma bonding system, which is inductive, can either stabilize positive charges or negative charges, and therefore plus and minus I. So if you draw several resonance structures of aromatic compounds, simple aromatic compounds, you immediately see that they might have interesting properties. For example, fluorine, as the most electronegative element, as also can be seen by the dipole moment, which is clearly directing into a certain orientation, can lead to delocalization, so that the lone pairs on the fluorine might also be delocalized over the benzene system. And indeed, if you do the reactivity studies in aromatic chemistry, and this has been known long before Hammett studies, it is indeed the case that fluorobenzene is slightly more electron-rich than benzene itself, because it experiences resonance effects, the plus M effect of the fluorine substituent. So necessarily also for oxygen substituent, this holds true. And if you go to the other direction, for example, taking strongly electron withdrawing moieties like nitro groups or cyano groups, you can see that now the electron density is being pushed out of the aromatic ring system. So delocalization occurs even into the outer oxygen atoms, and thereby the ring system will lose some of its electron density, and it leads to an electron deficiency. Same holds true, of course, for cyano groups. Nevertheless, polar effects also for these four substituents or functional groups, as you can expect, because they are always consisting of more electronegative elements than carbon, that the polar effects are relatively clearly oriented into one direction, going from the electron deficient or more electron deficient carbon atom to the heteroatom, which is more electron withdrawing, and therefore you have this dipole moments. Yeah, and therefore one can also have indeed an overlay of resonance and polar effects. And usually what we also see in organic chemistry, and that's the basis of electrophilic aromatic substitution, also the retroselectivity in electrophilic aromatic substitution, it is more or less dominated by the resonance effects. For example, with the methoxy group, you will have the para or ortho substitution, as you know. Okay, so I told you about the Hammett treatment, that one can also see the correlation between either the logarithms of the structural parameters coming from the pKa, or the corresponding reactivities coming from the rate constants, in the sense as a correlation with the substituent parameters named linear free enthalpy relationship. And there you also saw that there is this rho value. The rho value tells you as a reaction parameter what is the effect of the polar substituents. And you can imagine that there are three different kinds of cases. First is if rho is significantly greater than 0, then you can see, first of all, there is a sensitivity of a reaction towards polar effects. You can also derive that the equilibrium constants will increase with electron withdrawing substituents, that the rate constants will increase with electron withdrawing substituent. And this tells you, in turn, that there is a negative partial charge developing in the transition state, which we usually consider to be anionic or carbanionic in its character. If the opposite is true, so rho is significantly smaller than 0, then you can also say, yes, there is a sensitivity towards polar substituent effects. K increases now with the opposite. Electron releasing substituents help in shifting the equilibria. They help in increasing the rate constants. And this tells you that obviously positive charges now are developing in the transition state, which we usually assign to cationic character or carbocationic character if it happens on a carbon atom. And then we have the third case where rho is not, where it's 0. Then you can really say there is no sensitivity at all for a reaction towards polar substituents. In these cases, you can really derive that polar substituents will not have any effect on the reactivity, on equilibria whatsoever, because they belong to the field of unpolar reactivity. And this makes a difference, of course, and therefore we can distinguish between polar and unpolar reactivity. And now, of course, on the basis of linear free enthalpy relationships, we can also do that on a semi-quantitative fashion. So what does now a linear correlation mean? You do your experiment, you collect your data, you determine rate constants, you plot now these logarithms against the substituent parameters. What does a linear correlation mean? What does a non-linear correlation mean? And eventually, what does it mean if you find a discontinuity? So if, for example, simply the slope all of a sudden changes into another direction. So let's start with the first aspect. If the log kx over k0 correlates linearly with sigma, then you can tell over the whole series you have been looking at, they all follow the same mechanism. This is particularly also interesting if we now then go later on to chromophores. What does mechanism mean in this case? So I can already tell you this means that's the underlying chromophore, because sometimes also chromophore interactions might change, and also chromophores also can be dominated by other effects. If the correlation is nonlinear or curved, then you have an indication that there is a change of the mechanism that happens gradually, not all of a sudden, but also it can mean that side reactions are going to develop. And this is also an important aspect to consider. And most importantly, then, if you find a discontinuous relationship, then it tells you that the mechanism changes abruptly. So all of a sudden, mostly at a point where the electronic information obviously now is a different one. If it's not the stabilization of a positive charge, but a negative charge by the substituents being employed, then this might have a crucial role on the outcome. Okay, so summarizing, rho being smaller than 0 means electron deficiency at the reaction center in the transition state, and therefore plus M plus I substituents are favorable. Rho is greater than 0, then an electron excess needs to be accommodated, and therefore you need to have electron withdrawing substituents like minus M and minus I substituents, which are particularly favorable. And all this has, of course, been collated in table works over pages and pages. Books are full of them because the physical organic chemists have, of course, done a lot of investigations. Also, refinements were done. So I will quickly go through some of these parameters that have been enlisted here. Here you see the substituents associated with that also, for example, silyl substituents are available. Also ammonio substituents, positively charged nitrogen is available, and so on, cyano, nitro, you name it, whatever. And there are, of course, many different values. So first, of course, we have to take a look at the extension of the row system. So there's not a single, the sigma system, there's not a single sigma parameter. The original parameters were derived from Hammett himself as sigma p standing for para substituted and sigma m standing for meta substituted benzoate aromatic derivatives, which are, of course, then be found here in the first two columns. However, it was very quickly discovered that if you have discrete charges developing, like positive or negative charge, you need to take care. Then you will have to also to take a closer look at that the substituent parameters might change. So a substituent can have a significantly more negative value as a sigma plus in comparison, for example, to the sigma p value. So the sigma plus here of in the first case, that's acetoamido. So that's this amide substituent with minus 0.6 means that it's already pretty good in stabilizing negative charges, positive charges. Yeah. Which of course can be also then followed with a dimethylamino. It's even more negative. So this is very favorable. And in turn, you can also take a look in the other direction. What does an acetamido group, for example, mean for stabilizing negative charges? So it also can stabilize negative charges because then it needs to be more positive. But you can also see that there are substituents like, for example, diazonium, which account for 3.43, that they can perfectly stabilize negative charge. But of course, as you can see, because that's here it's void, there's no stabilization of positive charge whatsoever by a diazonium. Therefore, there are different types of substituent parameters. And in addition, also was introduced that there an inductive sigma parameter, the sigma I. So that's here the forelast column, and also the sigma R, which is a purely resonance effect, which you can see. In some cases, you see that they are not that extremely different from certain initial Hammett parameters, but of course, they mean a refinement of the treatment. And for example, Yukawa and Tsuno have constructed a coupled equation where they have two different types of parameters, that's sigma x and sigma x plus, also to take care of the relevance of a stabilization of positive charge. And then they have introduced a weighting factor, that's the R plus, what you have in there. So let's simply make a thought experiment. If you have no stabilization of positive charge whatsoever, then this second term here in this equation will fall off. And then you have the regular Hammett equation, that's the correlation with sigma x. So the substituent parameters are perfectly correlated with the rate constants. Let's go to the other direction. You have a full positive charge that develops. Then this means that R plus is 1, the weighting factor is 1. And if you simply then solve this equation, then this tells this will fall off, it will be subtracted. Therefore, it only will depend on the sigma x plus. And as you can also imagine, there are also cases in between. And to be more precisely then, especially Taft and his collaborators here in this very comprehensive review in chemical reviews on the Hammett substituent constants and resonance and field parameters, they have begun to create dual substituent parameter equations where you have also two different types of rho values, and rho I and a rho R. So simply also telling that the world is more difficult than simple models suggest. And even this kind of 4-parameter equation is also possible where one really tries now to take care of all different kinds of aspects like resonance with sigma R and polar substitution with sigma F. but also as aspects with such as electronegativity and also polarizability constants can be also introduced, and thereby one has the possibility of really getting a refined description and of course a better correlation with the data one can mine from the experiments. Okay, so that was quite something about physical organic treatment in general of reactivity. Now let's take the jump to chromophores. So if we're dealing with chromophores, it's also needless to tell you that they will be affected by substituents, because substituents might either push electrons out, push electrons in, or pull electrons out of a pi system, and thereby changing the electron density on the delocalized structure. And this has, of course, significant effects on many electronic parameters, such the absorption will be affected, and closely related to absorption is emission, because it's often a consequence of absorption. And also, if you only take a look at the ground state, it's also the redox potential that is affected. So if you take these four chromophores, that starts with aniline, nitrobenzene, paranitronylene, and metanitronylene, you see that their UV spectra apparently are quite different. So in the case where you have the para substitution, you see a quite dominant absorption band at 350, where in the case of the meta substituted derivative, you only see a relatively weak absorption band, also around 350, 360. And for the two more or less constituent moieties like nitrobenzene, which you can also discover in both of these later chromophore systems, and aniline, you see that their absorption maxima lie in a region that is already deeply in the UV. So they are not coming close to the visible, which usually starts around 400, as I also told you in my last lecture, that we have a visibility window which is between 400 nanometers and 800 nanometers. Okay, we can also, as organic chemists, relatively quickly think that if we have a para or else an ortho-substituted derivative, we can easily come up with drawing resonance structures. And if we have resonance structures, this means also electronic stabilization. And usually this one is, in the case of the paranitronylene, is named the aromatic or neutral resonance form. And this one, because it looks a bit like a quinoid system, it's called the quinoid or zwitterionic resonance structure. This is, of course, dependent on the substitution pattern. So if we take now a look on these kinds of chromophores, so a series where one has a styrol imidazole, which contains also dicyano substitution at the heterocyclic end. At the other end, there is a donor substituent. So now you can see the effect on the frontier molecular orbitals, because ultimately, of course, things will depend on the positioning of the orbitals that lie between the occupied and the non-occupied, so the frontier molecular orbitals. So if we take the unsubstituted system, means D equals H, you see the HOMO lies significantly lower than in case of donor substituted derivatives, where you see with the methoxy, it already shifts up by something like 300 millielectron volt, and even by 1 volt, it shifts up by 1000 millielectron volts in the case of dimethylamino substitution. Thereby, you will, of course, change the positioning of the HOMO. On the LUMO, you also see some minor effects, only a very minor effect. As you can see here, it more or less lies, everything lies between minus 2.6 and minus 2.8. So in a very, very narrow margin. And this has to do, of course, with the coefficient density of the position where the substituent is being placed. So if there's a knot in the molecular orbital, and we are now looking here at the LUMO, then of course the substituent will have no effect on the positioning of this orbital, or let's say it will not have a resonance effect, and therefore you will have more or less very similar frontomolecular orbital energies. Okay, and this can be also being depicted here, what you can see here in this case. So if you take blue is the part of the LUMO part, red is the HOMO. Usually the colors red and blue are taking to our feeling of water. So warm water is usually associated with red, with heat, and cold with blue. And therefore, one could really see that with donor substituted moieties, it is on the benzene part of this chromophore. You have the localization of the electron density, and in the LUMO part, everything is more or less shifted to the acceptor end of the molecules because we have dipoles in these cases. So that's the ultimate effect, what you can directly see. Yeah, and these kinds of donor pi acceptor systems, of course, are the prototypical chromophores, as I also told you last time, because most chromophores are being constructed on this kind of principle. And now you can imagine what kind of possibilities you have by the substituent pattern to effect electronic changes. And that you could do by tuning by the donors. So if you place donors to the systems, you can also tune the pi electron system. So not only bithiophene, but also tolanes can be taken. Or eventually, as you can also see here, these quinoid systems also could be taken as pi systems. And then, of course, the acceptor moieties, which can be varied and thereby also affected. So these three parameters, structural parameters, can be affected. And this has been done, for example, in the case here of tuning the donors in nonlinear optical systems. Nonlinear optics is particularly interesting because usually you're operating also with high electric field strength, which you usually only have with lasers. And that was the reason why the NLO effects were not being discovered before the advent of laser. I mean, there have been a lot of theoretical work, and which also predicted there will be something like nonlinear optical effects. But of course, you need to have higher powers of electric field, and that's what you only can achieve with a laser. And the reason for that, I'm not a deep mathematician, but I only can very quickly share with you what I've learned so far. It is a Taylor series, which you can always have in describing how electron density is being shifted around in a molecule. And there you have first order, second order, third order. And of course, the coefficients that have to be multiplied are relatively small, and therefore you need to have high powers of laser. And because it goes then in the E square and E to the third. And these are, of course, then leading to effects that are nonlinear, and therefore one speaks about nonlinear optics. And one possibility, for example, is to take a look at the change of dipole moments. So in certain cases where here are the numbers given for these compounds. If we take the bithiophenes, you see by going now to stronger donors, you can create relatively significant changes in the color, and the color also plays a role. And then the beta zero value is the hyperpolarizability, the nonlinear optical coefficient. So the second coefficient, alpha, will be the polarization. So this is then the next one, the hyperpolarizability. And then it leads to higher values. And this has been, of course, exploited vastly, especially in the 1980s. So 1980s, early 1990s, this was the high time for nonlinear optical research. And the problem was a little bit that people were too much looking for world records and to try to boost the numbers. And then, of course, very quickly also systematic mistakes appeared in the literature. And one of these mistakes was that any kind of chromophore was taken, and it was always looked on the frequency doubling, and if the doubled frequency is in the same region as the absorption, you can imagine that you will see resonance effects and not a nonlinear optical effect. And therefore, a lot of these data were false. Many photophysicists were disappointed, of course, but then they became very careful. And also, as you can imagine, for this highly topical field, the interest was also then a little bit lost in that. But nevertheless, there are some important applications one can use with nonlinear optical effects, for example, like photorefractivity. So you can change the photorefraction of a material by putting on a voltage, and this means an electric field. And thereby, for example, you can change the behavior, the optical behavior of materials. And this, for example, gives you certain starting points. And if you play further with this game, what nonlinear optics will allow, not only frequency doubling, but you could also use frequency sum generation and rectification. And ultimately, this means you could calculate with light at the speed of light. And this makes it interesting because it tells you that something like an optical computer should be feasible on these principles. Nevertheless, this has not been built yet. Okay. Another aspect which currently is also very hot is dye-sensitized solar cells. So this is the abbreviation. So very briefly, this means you irradiate a chromophore with light. You will find charge separation, as you also see with photosynthesis. So a separation into a radical ion pair, so radical cation, radical anion. And the electron usually can be very quickly translocated to a photoconductive layer, and therefore you are then generating something like a photocurrent. And this, of course, this is very important, as you can also imagine, because you can convert directly sunlight into electricity. So that's how photovoltaic works. Most photovoltaics is operating on the basis of silicon, and the silicon has, of course, very favorable properties because it's semiconductive, and not only semiconductive, it can also be made photoconductive, and that's what we have on our roofs if we have a photovoltaic system. But nevertheless, what Mother Nature has learned over billions of years is that one can also use organic chromophores, like, for example, porphyrins and these kinds of structures, or even simpler systems. Again, we are in the realm of donor-acceptor pi systems, as you can see here. So in some cases, one has privileged binding motifs to the surfaces, like these cyanopropionic acids, which are being condensed to give double bonds, so conjugation pathways between the donor edge and the acceptor edge. And here it is ligated to a photoconductive surface so that the charge separation can be immediately converted into a charge flow. And you can also see some of these data that came from DFT calculations. So in many cases, one has standard functionals and also basis sets that are being used for calculating the frontomolecular orbital energies. Thereby, one can estimate an optical energy gap, so the difference between HOMO and LUMO, and this more or less is the energy you need to absorb, and this correlates, of course, with an energy of the chromophore. And if you measure the energies of the chromophores, so absorption and emission, you can directly get these kinds of data, and then you can compare it with the calculations if the model that was taken is correctly giving these information. And yeah, and it tells you, this gives you a possibility of harvesting sunlight by this kind of photo excitation. But you need to have, let's say, a strong degree of charge separation. Okay, tuning the pi system. I already told you that this is always a possibility of affecting chromophores. And one possibility, of course, is changing what is in between donor and acceptor moieties. So this can be either nothing, this can be a phenyl ring, this can be a styrol moiety, this can be a biphenyl A stilbene and even toluene, and thereby you can then do all kinds, mine all kinds of informations how things are changing, not only with respect to absorption, also with respect to nonlinear optical effects, as you can also see here, this can be affected. And most importantly, what you always will start with is the optical spectroscopy. In the absorption spectra, you also see immediately what happens. So on first sight, if you take a look at a chromophore, you can see if it's either colorless or if it's colored. And if it's colored, you can immediately say, okay, the absorption obviously happens somewhere between 400 and 800 nanometers. We have talked about that last time, which color lies in which regime. And thereby, of course, it's important to record spectra simply to get information on the energies. And then, of course, if you're doing that in solution, you need then to also choose a correct solvents model if you want to perform calculations for comparison or also for assignment and sometimes also for improving. So in all these systems, what you see here, it was always the same donor that has been placed. So the dimethylamino was the D that has been implemented here. But this is also important that you not turn all screws simultaneously, but rather try to take a series where you leave something constant. That can be, for example, the donor, it can be the pi bridge, and it can be the acceptor. And therefore, you have the possibility of going into systematic studies. And as being said, of course, also the acceptor can be tuned. It is not only the aldehyde, it is also the dicyanomethyline that can be chosen, as well as this thiobarbituric derivatives. You can also play around in terms of the aromatic to heteroaromatic, also expanded fused heteroaromatic systems. In many cases, the elongation also by condensation can be achieved, as you can see in these derivatives of thioindigos. Also, these types of symmetrical structures where you have the possibility of left and right differentiation of the substituent, what you can use. And of course, in many cases, always carbonyl derivatives, which are relatively strongly electron withdrawing moieties, and thereby you can easily control the polarity, the polarization, and also the hyperpolarization of the structure. Again, this also has been exploited, as you can see here, for nonlinear optical effects. And here, the relative value coming from the EFISH measurements also amount very significant numbers, as you can see here, in a very deeply colored system. So 64, it's this kind of symmetrical bichromophore. And if you place as acceptor moieties these at the two termini, then you will immediately see that it leads to a significantly redshift in the absorption and also to a significant effect. And simultaneously, because all of these dyes are materials, you can also determine certain properties of the materials, like, for example, the melting points that can be followed, or also sometimes phase transitions if this is desired. Yes, and now you can also combine both donors and acceptors. So here I've collated some aromatic donors, also organometallic donors. Ferrocene also has entered the arena, as well as so-called pro-aromatic systems. Upon delocalization, they obtain aromatic character, therefore they have been called pro-aromatic. You also have malonic acid derivatives, especially malonitrile is a relatively strongly electron withdrawing moiety, but also it's cyanoacetic acid derivatives, barbituric acid, as previously told, and also these indane diones and their condensation products. You can also choose cationic acceptors. They drag more electron density, as you can imagine, like either pyridiniums or benzothiazoliums. and even also benzoimidazonium salts. And of course, heteroaromatic systems where you now, by placement of nitrogen atoms, you will make them significantly more electron deficient. And this then also causes a stronger electron withdrawing effect. In some cases, for example, we also use this kind of acceptor. This is more or less an expanded malonitrile, if you wish. It is embedded, so the structure is rigid. 3 cyano groups are dragging electron density like hell, and this, of course, leads then to a maximum effect with respect to the polarizability of the system, and therefore it leads to deep color. Okay, so now we can switch gears, and I would like to tell you first about what I chronologically did first in my academic career. So coming back from my postdoctoral time in the United States, I was very interested in benzene complexes with chromium tricarbonyl moieties, because it was already shown in reactivity studies that the chromium tricarbonyl moiety behaves essentially like a nitro group on the benzene, but it is not attached like the nitro group. So it is not bound to the sigma framework, but it's rather coordinated as a pi complex. And simultaneously, which makes them even more exciting, and that also attracted my attention, not only the stabilization of negative charge, either, for example, here in benzylic position, or if you attack by nucleophiles the ring, but also the opposite. You could also have benzylic cations. And this is quite unusual, because why should a tricarbonyl moiety be able to stabilize positive charge? And the reason is quite simple, because if you take a look, what is the oxidation state of chromium? It is 0. And this tells you it has all its d electrons available. So it can be considered with this respect as to be electron rich. And that is the effect why chromium tricarbonyl benzene complexes not only can stabilize benzylic negative charges, but also benzylic positive charges. And as you can also see here from the title of my habilitation thesis I submitted at the University of Munich some 22 years ago, almost 23 years ago, it was about these kinds of complexes bearing conjugated substituents as a new approach to organometallic chromophores and electrophores, because of course one can also fine-tune the electronics by remote substituents coming from the side chain. So here I was really working on developing systems that are electronically amphiphilic, so they can behave as acceptors or donors depending on what you offer them on the opposite side. Of course, there was first a lot of synthetic chemistry to be solved, so there was no precedence for these systems. I had to invent synthesis and also apply certain methodologies, and then finally to establish their chromophore character and also their electronic properties with cyclic voltammetry. So I will only give you a short look into this. So I started up with alkynyl derivatives. So this looks very simple, of course. It also did not take me too long of a time to synthesize the compounds. Nevertheless, there was no Sonogashira coupling on chromium carbonyl complexes, so this had first to be developed. But once I had the protocol in hand, I could do a variation of all substituents here on the alkyne, going from electron poor to electron rich, and that already set the stage. So it was possible also to take a look at certain aspects, for example, the differences in shifts here. What is being in the literature is being named the delta pi, so the chemical shift of the para position and the meta position. And you can also see that this changes in dependence of the substituent pattern. What you have here, sigma p, sigma I, sigma r, and sigma p plus, I took for correlations and took also what happened there. And furthermore, as another measurable magnitude, I took the carbon NMR shifts of the carbonyl signals because they were nicely found as singlets in the carbon-13 NMR. And in addition, of course, then the optical data in 2 different solvents. So also to see whether there is solvatochromism. There is some, not too pronounced, but there is some solvatochromism. So, and this then, of course, led to the corresponding correlation studies. And here I share this with you. And you can see that also chromium carbonyl complexes can be brought into linear correlations. And some of them are quite good. Some of them are not as perfect as one might think. But what can be extracted now from these linear correlations? So the plot again of, for example, the carbonyl resonances against the delta P or the sigma P parameters. And here the correlation of the absorption maxima against the sigma P. This is a nice correlation, as you can see here, as well in dichloromethane, as well as in acetonitrile. So what could be derived from these correlations? So I've collated it here for you, that the remote substituent effect on the other end of the molecule has an electronic effect that is transmitted through an alkynyl bridge, okay? And it even goes out to the carbonyl groups. That's what it tells us by inductive and resonance effects. And why is so? Because it is a sigma P correlation, and sigma P consists, I have written that on a previous page, it consists of inductive and resonance effects. It's not purely a resonance based substituent parameter, but also to some extent on its inductive effects. The second is here from the optical spectra, that is the so-called MLCT band. That's a metal to ligand charge transfer. So the metal gives energy into the ligands, and that leads to an absorption. And it is also affected by remotely by the substituent patterns, again, sigma P correlation. And indeed, what one also sees that there is a negative solvatochromism. This means in polar solvents, the absorption maxima are blue shifted. And this tells us that the phenylchromium tricarbonyl has a special electronic effect. And it is indeed acting as both, as an electron acceptor and as a donor. And that also made then the theme of my habilitation, that it is electronically amphiphilic. Okay, now let's switch gears. Let's go to phenothiazines as a strong electron donor. So we are taking now completely one side, which means strong electron donating effect, very electron rich. Phenothiazine is depicted here. So this is the IUPAC numbering according to the Hansch-Wittmann-Patterson system. It is a non-natural compound. It is industrially produced on large scale. The synthesis goes back to August Berntsen in 1885, and it can be obtained by a condensation of diphenylamine with sulfur at higher temperatures. Later on, that was also reported by Berntsen himself. The improved synthesis was to perform with iodine catalysis at lower temperatures, the same synthesis. So phenothiazine then quickly became important in the so-called sulfur dyes. Berntsen was a BASF chemist, and thiazine dyes like methylene blue, for example, which was first synthesized by Heinrich Caro, methylene violet, or also the Loth's violet or thionine, are derivatives of phenothiazine. And of course, for a long time, this was a very dominant application of phenothiazines to be constituent of dyes. Then, in the early 20th century, late 19th century, Paul Ehrlich was discovering the effect of chemotherapy, that you could treat certain diseases by administering small molecules. And if you ask me, this is, of course, the birth of pharmaceutical industries, because all these dye companies that were created in all countries in the world then immediately shifted their interest and also their business model towards pharmaceuticals. And indeed, methylene blue has also been tested as a quite efficient anti-malarial agent. However, the name blue tells you that there is a problem. If you administer that, of course, your skin will take a blue color. And nobody wants to have a blue color. And therefore, it was never considered to be as a remedy against malaria. But it is pretty effective, and it also has been systematically studied in vitro against certain development stages of the schizons, which are responsible for the development of malaria. Then phenothiazines became part of especially psychologically active drugs. So many of them have certain effects on the CNS, on the central nervous system. And of course, this second pre-life phenothiazines has been then later in, I would say, in the late 1980s, it has been shifted against to physical chemistry because it gives nice signatures, and that has to do, for example, with its ease of oxidation. So it can be oxidized from the native state to the radical cation state. This simultaneously is a change in the structure because the reduced phenothiazine has a butterfly structure, so it's bent here, therefore like a butterfly. And if you take out an electron, the radical cation is perfectly delocalized, which also has been shown by EPR spectroscopy and also by X-ray crystallography, that is fully planarized. So there's also a conformational change upon oxidation. Therefore, phenothiazine became interesting as a probe for electron transfer studies, and also, and I think we also contributed to that as a constituent in modern chromophores with respect to organic electronics and their applications. And that's, of course, where our interest in these compounds began. I would like to share with you one work we published in Organic Chemistry Frontiers 2 years ago. My two doctoral students, Laura Meyer, who graduated this year, and Lars May, who graduated in 2000, were doing a study on phenothiazines with N substituents. They can be easily synthesized. I don't want to go into synthesis here, but Buchwald-Hartwig coupling of phenothiazine with any kinds of aryl halides is possible, and thereby creating the substance library. So the interesting thing, however, is what you already see in X-ray structure analysis. It really depends on what kind of substituent you place on your aromatic substituent that sits here on the nitrogen. So there are two different kinds of conformations phenothiazine can adopt. One is called intra, because the substituent more or less points towards the plane, or let's say the environment where all these aromatic rings are lying, or extra, where it is more or less like in an axial position. So this would be equatorial in an axial position where it points out away, so extra. So these two types of orientations, both are satisfying the problem that if phenothiazine was planar, it would be a 4n pi system, therefore a Hückel anti-aromatic system, and nature always tries to escape anti-aromaticity. And therefore, the system folds, and with this folding, this butterfly structure, two different conformers can evolve, extra and intra. We were quite surprised that there was no systematic study on whatsoever can be used to explain what is the factors that are determining, because what we immediately saw going through these kinds of substituent patterns, there is obviously a transition that happens. And first we did TDDFT calculations for two reasons. First of all, because we were operating on the ground state. A statement by the late Paul von Ragé-Schleyer, one of the giants of computational chemistry, he said already in the early 2000s, he said a good DFT calculation is as good as an X-ray crystal structure analysis. So there's no big difference between. And even as an experimentalist, I have to admit that is kind of true, because the quantum chemical calculations based upon this model on the ground state, the DFT calculations are relatively precise. So we chose, in this case, the B3 lip as the functional and a relatively advanced basis set to describe also diffuse and also further actions of higher elements. And we also chose a solvent model, because ultimately we wanted also to go then in correlation studies with physical properties we can measure. And first thing what we found is, in doing so, Lars did these computations, he found that there is an equilibrium you can establish between intra and extra, because there has to be an equilibrium. You always will see one average species in NMR spectroscopy. So in NMR spectroscopy, obviously they can interconvert relatively quickly. Therefore, we also checked one time ago, we tried to check how deep can we go into temperature to get a resolution into intra and extra conformers, but even at minus 140 degrees, it was not possible. So we did not see anything. So I mean, there was the typical broadening of the lines according to viscosity, but no, there was no coalescence or whatsoever. And therefore, we did a computational approach here and calculated both, in each case, both the intra and the extra conformer, their energies. We did the treatment thermodynamically correct with 0-point correction and so on. And we finally then found that the energy differences gave rise, what you can see here, to the equilibrium constants. And the first thing what you see here is that there obviously it makes a difference if you have an acceptor where the extra conformation is dominant, vastly dominant, as you can see here, 99.3 to 0.7%. And that changes then over cyano trifluoro if you go to the more electron-rich, where then all of a sudden the intra-conformation prevails. So if you have electron-rich substituent, you will adopt this intra-conformation where you have a pseudo-equatorial orientation. And also you can see here from the K values, this then tells you we are then beyond 0.1 for the extra to 99.9% for the intra-conformation. So, and here you see that these calculated data, these delta G's, the energy differences, they can be plotted against the sigma P. It gives a nice correlation. So at least the Boltzmann distribution obviously can be correlated with a physical output, that is the oxidation potentials. Yeah, and then we also went on further and correlated the oxidation potentials against the sigma P's. And here you see there's a perfect correlation. So we are above 98% in its R-square value. So that this means we can take then also unknown derivatives, or let's say also unknown substituent parameters, by simply measuring their oxidation potential, which comes from the oxidation to the radical cation. And then we can determine the so-called sigma P, which we did in this case because we used this equation. For example, we wanted to know the hexyl substituent at this position, or the bis-anisole amino substituent, or the N-pyrrolidonyl substituent. They were not documented in the literature, and we did so by recording the cyclic voltammograms, the oxidation potentials, and thereby we could then evaluate what the sigma P values are. So we have now for our future studies, of course, these sigma P's available. Furthermore, we were also ambitious and we thought, if it's possible also to tell something about the excited state, and the excited state can be best described by fluorescence spectroscopy. So what you see all of a sudden is a solvatochronicity of a phenothiazine compound. So going from left to unpolar, from unpolar to polar on the right, changes the emission color. And this can be also then blotted, and it is done by the so-called Lippert-Mataga plot. So here you see it is the CF3 derivative. So R is CF3 that has been chosen. By taking the Lippert-Mataga treatment, one can then evaluate the change of dipole moment. If you assume that this is a spherical dipole, you can do some kind of calculations, which tells you something about the so-called Onsager radius. So this is Onsager's dipole theory that has been employed here. And thereby the dipole moment can be calculated to be 14.2 upon photonic excitation. That is the change of dipole moment, what you have if you go from the ground to the excited state. The TDFT calculations, when you perform then of these molecules, they show you that the longest wavelength absorption band has a significant charge transfer character. So this means the donor system, the phenothiazine, is locally excited in the phenothiazine core. However, with an acceptor substituent like here CF3 nitrocyano, then you have a change of the chromophore, and it tells you that you will get a CT character, a charge transfer character for these systems, also depending on what kind of systems you have. And we even went further, and that was Laura Meyer's achievement to perform first the synthesis of these diaryl substituted phenothiazines, so in the 3 position and in the 10 position on the nitrogen. And because there you have, of course, effects from both sides, the remote effect and the direct effect, which will then tell you something about intra-extra relationships. And of course, these systems were then put into a correlation. So this is a planar correlation because we get a plane in the end. It's a 2-parameter correlation where we see that the R1, that's the remote substituent, correlates with sigma p plus. So it's the delocalization of a positive charge over the pi system. And the R2 at the nitrogen substituent in para position correlates with sigma p that operates through the inductive and resonance system. You can see also from the slopes that the effect of the latter is higher than the former, approximately by doubling the effect if you go then from the remote effect to the direct effect, and thereby you can of course then determine this correlation plane, and this allows you then of course to take certain potentials and see how they can be, for example, being composed of different sigma p's, and then you can make a suggestion what kind of molecule you will have to synthesize. Here again, the correlation of the N-aryl substituent. So we left now this one constant. And here we did the variation in the consanguineous series, only varying R2. So what we see here on the absorption and the emission spectrum, that they perfectly give linear correlations. They give a strong correlation with sigma p minus. So telling that negative charge will be stabilized by this effect. So this means the donor will donate electron density towards the remote substituent, and of course this is more pronounced, gives lower energies if it is a stronger acceptor than, for example, methoxy. On the other hand, we also could take a look on the efficacy of fluorescence, so the efficiency given by the fluorescence quantum yield. Here we again see a perfect correlation. However, only four values were available to us. So of the fluorescence quantum yields on the sigma p minus, and this more or less also tells you that you can, here you see the substituent effects, that you can of course get more intense emission if you place a stronger acceptor to this position. And on the way to photovoltaic systems with phenothiazines, we were also interested in the electronic excited state structures. And here we took a look at the effect. I also showed this last time to you. So the upper presentation shows you this compound under daylight And if you switch on the UV lamp, then you see that's the fluorescence, and the emission solvatochronicity is quite pronounced. This could be seen also here on the right side. That's the absorption. On the left side, the emission. And thereby, of course, we can assume that it is a quite polar excited state, what we have to deal with. Simultaneously, phenothiazines tend to flatten out. And since we also had the possibility of investigating here remote effects here on this side by keeping the acceptor moiety on the other side constant, this gave us also the possibility of creating correlations with your oxidation potentials with a sigma p. So it is really an electronic effect, what we can see here by modifying here the substituent pattern on the oxidation potential, and of course what we also see here on the optical properties. And for the optical properties, also the comparison here between these two systems. So this is the unsubstituted merocyanine. This is an acceptor moiety on the phenothiazine, and the cyano-substituted. They more or less show a relatively similar behavior. However, what we found most interesting is by placing strongly electron withdrawing groups here, we could increase the fluorescence quantum yields. Also here, a correlation can be found. And this also then ultimately tells us that the system operates on a change of dipole moment that happens in the excited state. That is what the bottom line of these experiments are. And therefore, we did some calculations. Jan Schönhaber did that. Martina Haug, his later wife, she was doing the synthesis and all the measurements. And then we went into collaboration with Hans-Georg Kubal at the Technical University of Kaiserslautern, together with his doctoral student, Matthias Stolte, who did the photophysical measurements in the excited state. And we found some very exciting things. So you can see from these measurements, and also supported by the quantum calculations, is how the dipole moment changes. So it turns around, as you can see here, by placing another electron withdrawing moiety at the other side. And you also see what happens if you go from ground to excited state. It leads to a change in the bonding length of the different bonds. What you can see here, I've given several selective bonds. And this also tells you that besides a flattening of the system, so as you can see here, it flattens from 140 degrees. So this is this folding angle to almost 160 degrees, even above 160 degrees in the excited state. So this is the effect going from the ground to the excited state in phenothiazine. So we could experimentally also prove that and explain that also by theory. Yeah, and only some minor informations on the data here. One always has the comparison between experiment here in blue and theory. So for these both model systems, it shows quite nicely what is going on here, so that the computations give almost a good estimate for that what we finally observe then. And this can be also seen here in the UV-vis spectra that were done with the CT absorption bands. So this is the absorption bands and then the derivatives, and they can be fitted, of course, to the electro-optical absorption spectra in two different orientations, parallel and orthogonally. And this allows then, for example, by these informations to calculate the special effects on parallel versus perpendicular. And as you can see here, it matches reasonably with theoretically predicted or calculated values. So this led to a deeper understanding of the molecule class, and also what we ultimately learned from this molecule class is that we now can be able to construct photovoltaic systems with them, and that indeed happened. So here again, for illustration, here in black, you see the theoretical values, you see in blue the experimental values. Of course, there is some kind of displacement, which comes, of course, from the from the quantum chemical calculations, because it is always difficult to correctly describe the solvent effect, but you see by the parallel alignment that everything is in shape. Also, the change of dipole moments are okay. So these are scientific units. This is not debye, what you see here. And also, you can calculate the full cycle of excitation, relaxation, fluorescence, and relaxation back from the Frank-Compton excited ground state, and also what the energy values are here in between. Also, the Stokes shifts are quite precisely calculated with respect to that, what is being measured. Thing is that is more complicated is, of course, if you change then the chromophores, of course, expectedly the slopes will change. That's what you also will see here, because the acceptor effect here at the other end of the molecule certainly has an effect on the chromophore. And this is the things that are still most difficult to describe, because you can also see that the linear correlations here are not really good. They are in the upper 60%, but I would not call this a perfect correlation, definitely not, but only a qualitative orientation, what you can see here, so that the slope will change the effect. And ultimately what we are hoping for, that we one day will have a parameter to correctly describe also the acceptor moieties, like we can describe the donor moieties of phenothiazine. Okay, Valentin, what do you think if we make a short intermission of 5 minutes?
Yeah, of course.
Is that okay?
Yeah, it's okay.
Perfect. Then I would quickly,
yes.
I would quickly take a sip of tea, and then
Yes.
we will continue. What is your time?
33 minutes.
33? Then
Yeah.
at 40, is that okay?
Yeah, okay.
At 40. Okay. Yeah. See you in a moment.
See you.
So, okay, I'm back again. So if you are also ready, we can continue.
Yeah, of course.
Okay. Okay, now let's go into the other direction. Let's take a look at acceptors. And I would like to tell you some of our studies on coumarine derivatives. So here you see the coumarine core. So it's a benzopyranone. And we were particularly interested what happens also for synthetic reasons, because we could also establish some new methodologies here for assembling these molecules in a one-pot reaction. First on alkynyl coumarines, and then to take a look also on these donor substituted coumarines, where you have more or less an extended pi system in this direction, where the main chromophore is oriented orthogonally to it. I also gave you some information about coumarines. They indeed have a relatively broad pharmacological scope. It is itself, the coumarine, a secondary metabolite and also a natural product. It's often used as a food additive. So especially in May, it's very popular in Germany as the so-called sweet woodruff. Waldmeister is the German word for that. So if you have ever the chance to go to Berlin, you could, for example, drink a so-called Berliner white beer with Beschuss, and that's always Waldmeister, then it's green. And if you take raspberry, it's red. So it's a relatively sweet type of beer drink what you can have. And of course, here in this region where I live currently, it is the so-called May wine, also May Bowle. That's how it's called here in our language. So a typical drink for, let's say, occasions in springtime. Okay, but the thing is, coumarin is also toxic, so it has a relatively low maximum amount you can apply, and in food it's only allowed to have less than 2 milligrams per kilogram of food. And of course it has technical applications because there are many coumarin dyes, and they are being used as laser dyes. And therefore they are interesting because they contain the acceptor moiety as embedded as a lactone. And this means it is rigidified, so the system is planar. And of course, it is interesting with respect to generating something like myrcene, what you can see here. And for the first derivatives, the alkynyl derivatives, you can also see that you can play around with substitution pattern. You can get a shift of the color going from almost, invisible being in the UV with the emission towards orange emission if you have the corresponding substitution pattern. Moreover, they also show an interesting behavior with respect to aggregation, and that also caught our interest because we are taking also a look at effects like aggregation-induced emission, which is a transition going from solution to the solid state. And of course, this has some implications. I already told you about that in my scientific lecture in October. Okay, so here are the results from the alkynyl coumarins. Here, that's the way how they look in under daylight. Some of them are already to some extent daylight fluorescent. And this, of course, then intensifies if you then go further on to solution, also in different solvents. So this is daylight fluorescence, what you can also see here. And this is then the emission excitation with UV light. And since we have many different data, we could also then start correlations. And what you can see here, for example, is the substituent effects. Because substituents have sigma parameters, then you can, of course, plot the absorption, the emission spectra, and, of course, also the Stokes shift. The Stokes shift is the difference between absorption and emission spectra. And it is always given in reciprocal centimeters because it needs to be, it must be an energy linear unit which you are using for correlations, because the problem is that wavelengths are reciprocal with respect to energy. And this then, of course, gives some kind of odd behavior. Nevertheless, it doesn't keep people away from doing so. But if we do it correctly, you will use the correct units, and this will mean you have to convert your energies into for example, wave numbers. Also, you could use electron volts. That's the same. And thereby, you can now see what the effect is. Of course, it is a positive solvatochromism. It is an intense change of redshift if you go from a donor substituent to an acceptor, which you also would expect. So electron withdrawing substituent shifted, the Stokes shift somehow a little bit smaller to smaller energy gaps. Nevertheless, you see that the development is, of course, going to lower energies if you place electron withdrawing groups in comparison to electron neutral or electron rich groups. So this is the overall message which you can easily extract from there. And it already indicates a polar excited state, what you can see here. But if you want to scrutinize that, of course, you can also take certain substituents, if you leave them constant, and see what happens if you now play around with I have to go back again, sorry, to the other portion where you can do manipulations on the coumarin core. because then you can really exploit that you have two perpendicular pi systems interacting with each other. So this is more or less a series where you have constantly always the same, a so-called consanguineous series, the same substituent R1, which can be H or which can be, so here's also the variation here, or you can also switch around. And then, of course, this changes the color. And if you even do more so, then you can also see what is the effect if you change R1. So here we have three different changes. One, it's a strong donor, an intermediate donor, and no donor. And you see that the effect of the alkynyl substituent can also be seen on the fluorescence quantum yield. So with silyl substituent, you will get, in the case of R1 is a strong donor, almost unity as with the fluorescence quantum yield. So you can also play around with that, and which decreases if you go to, let's say, weaker electron releasing moieties. So this means the orthogonal orientation of the second chromophore plays a key role on the fluorescence quantum yield. That even becomes more dramatic if you take in comparison the phenyl substituent on the alkyne. A phenyl substituent, of course, has more degrees of freedom in terms of rotation and dissipating energy from a chromophore, and therefore you also see that with the H derivative, the fluorescence quantum yield has completely dropped. Yeah, and then this can be, of course, then further compared by taking a donor like diethylamino, so which has been identified to have relatively high fluorescence quantum yields, and then to do the variation out of the R1 substituent, that is the alkynyl substituent, to get insights what happens. And here you also see that the fluorescent quantum yield drops, not significantly because it ends here at 45%. So they are still luminescent. So it is really governed by the diethylamino substitution, but you can play around here, of course, with the sigma p value, and this indicates a donor substituent, obviously, on the alkyne leads here to a higher fluorescence quantum yield than an acceptor substituent, but you can see here from the sigma p value. Okay. Now, the second series which you could derive from these class were merocyanines. So if you remember from the last lecture, merocyanines are donor pi acceptor systems. So the double bonds represent the pi chromophore, and the amino group is the oxychrome, and the ester moiety of the lactone is the anti-oxychrome. So you have the typical situation of a push-pull substitution. And now, of course, you can play again the game with the substituent patterns here and here and here. So you have three sites where you can play. Of course, you will always follow a consanguineous series, not changing everything at the same time. But here you can see, for example, what kind of effect it will have if you play with these substituent as acceptors or donors in this position, and leaving the amino moiety in this one constant. Again, perfect linear correlations also allow you then to make predictions on the substituent effects, and most of them they can be seen that they do not match with the so-called Ewar prediction. Ewar's prediction says if I start a pi chromophore with the donor moiety, then it is negatively on the donor, it's positively, and on the next position, negatively, positive, negative, positive, and so on. And you would then expect, according to Ewar's prediction, that placing, for example, an electron donor at a positive moiety will then lower the frontier molecular orbital and will lead to a blue shift, so a stabilization. And obviously this does not happen. What we see here also two deviating orientations in absorption and emission. So emission goes down and absorption goes slightly up. So this makes it a little bit more complicated, and one can also then estimate, and especially if you take a look at this position here, that we have not the full range. So the dimethylamino is missing here. And that is on purpose because it does not fit at all in these correlations. And this can be explained because a new type of chromophore will be formed. That is the expansion of the pi system will create here a new chromophore that dominates the initial one that we have been considered. Okay, so if we then do, for example, calculations, we can also then explain that something happens with the orientations of the pi molecular orbitals. And one thing, of course, is that with increasing donor strength here on this edge, this then leads to the dominance of a second chromophore, which now is not a merocyanine of the classical type, but a phenyl expanded system. And this aspect can be particularly seen if you do correlations. You can then find these changes in chromophores. As I already indicated to you, changes in the slopes, discontinuities are interpreted in terms of reactivity as change of mechanisms. And here change of mechanism formally means a change of the underlying chromophore. And this can be especially nicely then seen with the quantum chemical calculations, which really can back up, because quantum chemical calculations, they do not care about measurements. They give the electronic structure as it is. And of course, it will always pick out, or it will always optimize into the direction where the most stabilization, according to the self-consistent field theory, will be obtained. Here I showed in this photograph that these compounds, because due to their rotational degrees of freedom, they also have the possibility of being forced into aggregation, and then they start to emit. And interestingly, you can also see that they undergo here a polarity shift. So because usually the experiments are done as such that you are dissolving the chromophore in a solvent where it solutes reasonably well, but does not fluoresce. And then you titrate in water. By titrating in water, of course, you're changing the polarity of the system. And by changing the polarity, this leads to aggregation. Of course, that is intended. But of course, it also has a polarity effect that then affects the emission. And thereby we also see this color tuning that can then occur by increasing contents of water. So here this pink type emission originates from a very high content of water. Okay, now let's switch gears again and go to indolones, because indolones are also acceptors. So this is the indolone moiety, what you can see here. And here you see three different types of structures we have been assessing over the years. They can be characterized as merocyanines, special merocyanines, also expanded merocyanines. Synthetically, this is another story, how we got them. We formed them by one-pot methodology, so by simply assembling using a palladium catalyzed insertion coupling procedure. But most interestingly, with this class of compound was when we held them in hand and put them into solution, they were absolutely dark upon excitation with UV light. So placing them under the UV lamp did not show any emission, but they emit strongly in the solid state. This was the first indication that this class of compounds is somehow pretty interesting. And later on, we also found out that we could indeed perform titration experiments and thereby also verify that these are AIE genes, so systems that undergo induced aggregation, and thereupon they light up, you see the emission enhancement. We first took a look at this series where here you see in the picture, under the microscope picture with UV excitation, that they fluoresce bright red. So an intense red, what you can see in terms of emission, but there's no emission in solution. That's the interesting thing. And we first took a look at the absorption data, because in the absorption data, you do not have to rely on emission, whether it appears or not. You simply start from the ground state, and you can try to map what is the effect of the substituents, what you can have here on the arrow moieties. And this has been done. It has been plotted against sigma p minus parameters. And there we found an interesting behavior. So when my student, Melanie, when she was showing these correlations to me, and she said, there's no correlation whatsoever. And then I said, just hold a moment. I mean, what is 4C? And then she said, yeah, 4C is the compound where you have a hydrogen at R2. I said, okay, if this is hydrogen and this is the maximum part, then on the left side, on the right side, you see a development if you change the substituents. And this, of course, will tell you something in terms of what kind of chromophores will be decisive. And indeed, it was the case that either placing here donors, so this is the left half, or acceptors will then lead, of course, to linear correlation. And you have here a discontinuity, an abrupt change in the absorption behavior. So on both sides, with donors and with acceptors, the values here are higher. This tells you are lower. This tells you have a redshift of the maxima. They are deeply colored. Only for hydrogen, you see it is the top where you have the lowest, the highest energy you have to use for excitation. And since, according to Hammett's treatment, this occurs at the position 0, the sigma position, sigma p minus 0, this tells you then obviously that you have a change in the chromophore. And here again, Dewar's qualitative perturbation theory. So if you have here the HOMO to LUMO gap, and Dewar introduced the so-called starring of systems, starting with the electronegative element, the nitrogen, you see that you have an alteration here. Stars are only at every second atom, and this tells you then you could have certain effects if you place then donors and acceptors at the unstarred position. So if you have an unmarked position and place, for example, here, and place here a electron releasing group, this will then lead to a lowering of the LUMO. Yeah. And if you take an electron withdrawing group and place him at the unmarked position, this will also lead to a lowering of the LUMO. And this tells you thereby you can see this kind of effect that the changing from unsubstitution to substitution gives you this development into the same direction. And we have exploited that with a certain system where we had a pyrazine at this moiety, a piperazine at this moiety, which was N-Block protected. That was also for other reasons, but we found this intriguing discontinuity. And this also explained to us that we have an abrupt change of the reaction parameter, which also indicates a change of the dominant chromophore. So all of a sudden, this dominant chromophore will become important if it will be here an electron donating moiety. So this will donate an electron density here into this direction. So on the way to these aminopropanylidones, what I've just shown you, we had as intermediates the aryl propynylidene indolones, so the immediate precursor. And in these cases, the compounds didn't show any solution luminescence, but as you can see here from the photograph, also tunable, they have emission in the solid state. And therefore, we became interested in exploiting this peculiar solid state emission. And we also found quickly out that it is favorable to have a tosyl substituent here. And then with keeping this substituent constant, for example, with the phenyl substituent, then you can also perform a plot and to see what happens with the absorption maxima, and they also nicely plot, and they correlate nicely with the sigma R, which tells you that you have a resonance stabilization over the whole pi system, and that it operates also in a resonance pathway. If you then switch to solid state spectroscopy, solid state UV spectroscopy, which we were generating by drop casting thin films on glass objects. And then we could also determine fluorescence spectra, which was also interesting to see that. And that gave us the possibility to determine Stokes shifts. And here you see also the Stokes shifts nicely correlate, but in this time they correlate with sigma p plus. And the sigma p plus correlation is of course dominated by the charge transfer state. So excitation leads to a shift of electron density from the donor to the acceptor, and therefore it has to be seen that at the other end a positive charge will develop, which of course will be favorably stabilized if you have electron releasing substituents, and that indicates the sigma p plus accommodating positive charge. That is the message of this chromophore, which is being generated in the excited state. So photoexcitation also changes the ground to the excited state in its structure and therefore also in its behavior. So on the last topic, I would like to tell you a relatively young series of compounds we have been establishing in the late second decade. So in 2017-18, we published our first works on, or let's say 2014 was the very first work, but a systematic electronic evaluation was following then 2017, 18, and 19. These are the three ethynyl quinoxidines. So as you can already see from this photograph, here you always see the same type of structure. It is an ethynyl triple bond quinoxidine, and with different substitution patterns, either here in the 2 position or here on the alkyne, you can do a rainbow color tuning of the emission color. And this is, of course, pretty promising. And therefore, we also went into a more systematic investigation. Also, quinoxidine, as many heterocycles, have a pharmaceutical pre-life. They are important constituents in pharmaceuticals, and also found many applications. But of course, their electronic properties makes them particularly interesting for materials, and therefore we went deeper in these studies. So what can you see here? So we took as a model compound for investigating emission solvent chemicity, because that's what you see here. This dichloroquinoxidine that bears a dimethylaminophenyl substituent as a donor. So this is the acceptor part, this is the donor part. And if you now put in the molecule into a solution of different polarities, solvents of different polarities, you see an enormous shift, emission solvent chemicity. So the stabilization of the excited state is determined by the polarity of the solvent. And this can be also then seen in terms of effects what the substituents can have. So here is sigma p plus plot of absorption, of emission, of Stokes shift, which also explain that you can play around with the certain decoration positions here at the position of the 2 substituent. Nevertheless, the advantage, of course, from solvatochronicity studies were that you could now determine the change of dipole moment by doing a Lippert-Mataga plot, and it was found that the changes with using a Onsager radius of 12.9, so this is an ellipsoid more or less, 26 dBi, which is quite substantial. In a later study, together with a colleague here from physical chemistry, um, stark measurements were performed with these compounds, and it was shown that their actual dipole moment is smaller than 26. It's just below 20. It's about 18 or 16, depending on the substitution pattern. So this means there's a systematic overestimation of the change of dipole moment coming from the Lippert-Mataga treatment. Nevertheless, the Hammett plot, the sigma p plus, shows you a redshift upon donor strength enhancement. So here on this side are the strong donors. And also that the Stokes shift, of course, increases with the donor strength, as can be also seen. So the numerical value gets larger of the Stokes shift with the increasing strength. And you can also see that the effect of the donor is stronger on the emission than on the absorption. That you can estimate. That's always the nice thing about correlation studies. You can do that from taking a look at the slopes, because this gives you a semi-quantitative estimation. And especially if you compare different series of compounds, you can directly extract this information. Okay, what can we do else with these kinds of ethynyl quinoxylines? We really loved the structure because it gave us a lot of possibilities, and by organometallic catalysis, we could also come up with a whole series of remotely substituted thiophene-bridged quinoxylines, where you also can see a relatively huge effect of the substituent pattern on the emission color. Here again, you see the Hammett plot. Again, as expected for the class of compounds, the effect on the absorption is smaller than on the emission. And that is then, of course, also seen in the Stokes shift, that one can also really predictively place certain substituents to achieve a certain spectroscopic behavior. Yeah, but besides also emission solvent chronicity, I don't want to go into this again because I just showed you they also show to be highly emission solvatochromic, what you would expect. You can also determine the changes of dipole moment using the Lippert-Mataga approximation. No, we became more interested what happens if we place here at this remote end donors which have some kind of conformational flexibility or rotational flexibility, as you see by this graph. And this, of course, then leads to a diminishing of the emission efficiency. So these systems which are emissive, if you have, let's say, unspectacular small donors. So here you can see then the effect like this. It goes to deep orange. Here you don't see anything if you have the stronger donor, the para-anisole. And that must have a reason, because the compounds are emissive in the solid state, as you can see here. They are, well, red emissive upon UV excitation. However, if you put it into solution and then titrate in water, or you can also embed them in methacrylate films, polymethacrylate films, then the chromophores are being rigidified. They are forced into aggregation if you are in solution. In PMMA, they are rigidified. And in the former case, this leads then to a light up fluorescence, what you can see here. So then the fluorescence begins to shine when these 3 degrees of rotations are being locked by aggregation. So aggregation is simply hampering this rotational deactivation pathway. And that's what we are investigating in many different chromophore systems. Of course, we always combine it also with some new methodology, because of course we love synthesizing molecules. And if we can do that by employing our philosophy of multi-component one-pot methodologies, of course we will do so. This brings me to the summary, and also thanking you for your long patience now in these more or less intense physical organic treatments. What can we learn from these kind of correlation studies? I've been showing you that Hammett-Taft parameters are well suited for establishing structure-property relationships. This has been already known before for organic reactivity, and that's a decent tool. And then you can do predictions, and of course on the reactivity. And our idea was, why can't we use this kind of physical organic treatment to make predictions on chromophores? The mathematical tools are simple. You can easily do them either by hand, or you use an Excel sheet. You can perform regression analysis. And the thing what you then can apply it to are absorption and emission data, which you obtain from optical spectroscopy. You can do that also upon variation of solvent polarity. This gives you additional information. And if you want to explicitly investigate the electronic ground state, then of course electrochemical data are very helpful, especially if you have systems that display reversible oxidation or reversible reduction, because then you can also establish that you have a thermodynamic equilibrium, which can always be returned back and forth, depending on the electron transfer in which direction it goes. Furthermore, it's also interesting for application if you have a switchable element inside. So the combination of dye chemistry and redox chemistry definitely can be also found out here. So cyclic volatimetry, of course, gives you a structure property relationship on the electronic ground state, because there it starts, while absorption and emissions spectroscopy from optical transitions, they tell you something about the excited state, and even more what happens if you are in the excited state, if you're going to return. So that's what the tool fluorescence spectroscopy allows you, and this gives us essentially a full picture of what is going on there with functional pi systems on a molecular basis. Yeah, with these structure property relationships, the correlations, we always start and we take a look at them, often quite unbiased. So we simply are curious to see what comes out. You can also unravel pretty unusual or also unexpected behavior. I've shown you examples of discontinuities, where you can, for example, derive then that something happens with respect to the dominant chromophore. You can also have, as you can have seen for phenothiazine derivatives, besides the linear, so one parameter, you can also have two parameter or even higher correlations, ultimately n-tuple parameters. And this ultimately gives us the possibility, because mathematics is not dependent on our ability of imagination, because you can treat mathematical equations easily. You can also start to employ mathematical methods also in a more advanced fashion, eventually also using artificial intelligence for making predictions, or also for evaluating the data that have been found. Okay, so I think I've made a plea for Hammett correlations. So this very old tool from physical organic chemistry is still very fruitful. It gives us insight into polar and polarizable organic and even organometallic chromophores. If you have substance library and if they are readily accessible, so why not doing so? And especially if you have diversity-oriented synthesis in your hand, then you can create, let's say, data sets which help you in understanding how chromophores are ultimately functioning and how they can be fine-tuned. And ultimately, which is important for application, how can they be optimized? Okay. Dušefan, Jakub.
Дякуємо. Thank you very much for your very interesting lecture. I think this lecture is important for PhD students of our institution, of course, and for master students and PhD students of Karazin University. Of course, we have in Karazin University physical organic chemistry course, but in your lecture today, you showed a lot of interesting examples of correlation analysis and application, practical application of this approach. So, dear colleague, do you have any questions to our speaker? No. Okay, so
everybody is exhausted in this cold winter days, I can imagine. Yeah.
Thank you. Very interesting lecture. Very.
Yeah, you're welcome, Victoria. You're welcome.
With pleasure. I listen with pleasure.